right? So 1/2 times 1.12 times omega is 2 pi over 0.86 squared times, and what's our amplitude? 0.48. Don't forget to square that, right? So 0.5 times 1.12 times the quantity 2 pi divided by 0.86 squared. This has to be in parentheses, or if you're doing it that way, times 0.48 squared. No laughing. 6.887 joules. Do you guys get that?
I get joules.
Yeah. You say joules, I say joules. I'm right. No, wait, it's the other way around. What's the total energy? Anybody want to give that one a stab? If the maximum kinetic energy it's got is 6.887, then what do you suppose the total energy is? 6.8. Yeah, because when it's got this much energy, if that's when it has this much energy, where is it? It's in the middle, and so it has how much potential energy? None. It has no potential energy. That's why it's the maximum kinetic energy, because it's gotten rid of all of its potential energy, turned it into kinetic energy, right? So that's that, and when it gets out to the edge, right, its total energy is now if you wanted to, you could use this formula for the total, which I actually pointed to first. It's the same one that we just used, but and I've actually had kids do that. Like, well, I better use this formula and get the same number. It's like, it's okay. Better than getting it wrong. Okay. And then it says, what is the kinetic energy when it's 0.23 from the equilibrium? Well, now we can use this guy here, right? Okay. So D, I'm going to use 1/2 times m, 1/2 m omega squared x naught squared, right? So that's 1/2 1.12 2 pi over 0.86 squared, and then it's it's 0.48 squared minus, is it 0.23 is where we are? Yeah. I'm so lazy. I'm going to go second entry, and I'm going to go back and put a parenthesis there. And then minus 0.23 squared, right parenthesis. I've got this in my calculator. I'm just adding like parenthesis. Yeah. So it was Lynn Spitz this morning was explaining what calculators you can use for ACT and not use for ACT, right? And she said that it can't have a CAS in it, which is like that, I don't know what it stands for. It's like algebraic, symbolic something, I don't know, right? And Greg Dinsey goes, oh, good, because I thought it sounded for close air support. Okay. What are we solving for? The kinetic energy, okay, there it is. Okay, 5.31 joules. Anybody else get that? So here's the kinetic energy at any given point. What if I asked you for what is the potential energy? What if I asked for what the potential energy is? Let's say D, letter 2 I's, right? Here's letter I, here's letter 2 I. What if I say, what's the potential energy at that point? Well, you're basically, if you're doing IB formulas, you're screwed, right? But couldn't you just do this argument, if that's the total energy, that's the kinetic at that point, what's the potential? Apparently potential energy doesn't exist for IB, for a spring, right? Can't you just subtract? Yeah. So the potential energy, this is a kinetic energy, right? The potential energy is just going to be 6.887 minus 5.31. I expect you to be able to do that on the skill sets and the whatever, but you should understand that. Okay? So that's 1.58 joules. Right? That's kind of crazy, huh? A lot of kinetic, not so much. And then part E says, write possible equations for its position and velocity. Well, let's say that it starts in the middle and it goes up, because that's what everybody assumes, right? That it's a sine wave, right? Okay, which is actually fairly unlikely, right? So x is equal to the x naught, so 0.48 sine omega, right? And we figured out omega is like 7.306, and then this just kills me, but we only have 2 sig figs, so we have to say 7.3 t, like that. If I was actually going to calculate it, I'd use the unrounded value of the omega, but here we have it. Do we have questions about that? That's exciting. Do we get it right? Yeah? 6.9. Yay. 5.3 joules. Look at that. I couldn't round it for the example. We got them right. I'm so happy. Let's have you guys try it.